Okay, so we are going to do Chapter 1, Problem 9 from Goldstein's Classical Mechanics. And just to read that problem, it says the electromagnetic field is invariant under a gauge transformation of the scalar and vector potential given by the following. A goes to A plus the gradient of the psi, which is a function of r and t. And then phi goes to phi minus 1 over c del psi del t. So the partial derivative of psi with respect to t. And remember, psi is this, it says psi is an arbitrary but differentiable function. Okay, so what effect does this gauge transformation have on the Lagrangian of a particle moving in the electromagnetic field? Is the motion affected? So anytime we're talking about electromagnetism, we should probably write down Maxwell's equations. So I'll just go over that really quick. So we have our so the gradient of E is 1 over epsilon naught times some charge density. We have the curl of E, which is equal to the negative partial time derivative of the B field, and then we have the gradient of the B field is always 0, that we know of. The curl of B equal mu naught J plus mu naught epsilon naught partial of E with respect to T. All right, so in electrostatics, this term here is going to go to 0. So we have this. So I'll just write this. Electrostatics the curl of this, the E field, will then be 0. And recall that anytime we have a curl of something being 0, we can rewrite that as a gradient. That's just properties of, because the curl of gradient is always 0, so we can write this here. And same goes with this term here. So we could write B being the curl of something. Since the gradient of B is 0, we can write B as the curl of our vector potential, because this is the velocity carrying information of potential, and that's why we need that. And so since we have, so then we can write the curl of E as this negative so since the curl of E is 0, we can also write it this way. See that? See how I just rewrote the B field in terms of this? And so we can write it like this. So therefore, E plus this is equal to this. Therefore, the full term is E equals our negative partial of A with respect to T minus this gradient of some potential, the scalar potential function. So this is how we can write our E field. This is important because it's going to be important for the Lagrange equations. And so it results that our full potential energy, and this is really, so this, where this potential energy comes from is just making it fit with the Lagrange specifically. So this is information that you really just have to know. You derive it from the equations of motion known in electromagnetism from the Lorentz force, but so don't get hung up on this too much. So this is our potential. This here. And so we're ready to go ahead and write our Lagrangian. So our Lagrangian equals t minus u, right? And that equals 1/2, just 1/2 mv squared. Nothing crazy. You can also write this as r dot squared. Let's turn this off. There we go. Same thing. And then you're subtracting this potential here. So you're going to minus q phi plus q a dot v. You can write this v dot a if you'd like. It really doesn't matter. Now, I'm going to go ahead and just introduce the, it's going to make it easier for our problem if we just, because the question initially is using our Gaussian units, CGS. So we're just going to convert this to CGS. Very easy to do. You just divide by the C here. Okay, that's all we're doing. And so now this is our original Lagrangian, okay? This is our original Lagrangian. And we're going to, now we have a new Lagrangian. We're going to call it L prime. And now we're going to substitute the rest in. So we have 1/2 m r dot squared minus q of our new potential. So it's going to be q phi plus q over c del of psi over del t. We're substituting this in up here, okay? And I'm also going to just go ahead and distribute it, but the expression's up here. Okay? Plus q over c, b dotted into a or vice versa, doesn't matter, plus q over c, and we're distributing the dot products. It's just a property of dot products. Del psi, and I think I have everything correct. Okay, good. Now immediately what you might notice, and let's see if I can use a different color here, is that this is actually inside of our new Lagrangian. So it actually, seems like a complicated problem, but it's not as complicated. So we have this, and this term are all of our Lagrangian terms. So let's start, let's just pick a different color here. And we'll do L prime equals L. It's our Lagrangian. So these terms, right? Plus Q over C, del psi over del T, plus Q over C, E dotted to the gradient of our psi. All right, beautiful. Now, what do we do from here? Well, it's actually just this trick where you just notice something about the relationship between these partial derivatives and a time derivative. And so we're going to show that relationship now, which is this. So if you have d dt, this is a full derivative. These are not del's. This is a full derivative of some function psi And this psi is a function of RT, remember? So with chain rule, this is going to be partial psi with respect to x, but we need the chain rule. So we're also going to have dx dt, right? And then we're going to have our partial of psi with respect to y, dy dt, plus partial of psi with respect to z, dz dt. And I think you're probably already seeing what's going on, but we also have this partial with respect to time. Now, this here is just a dot product. It's a gradient of psi dotted with velocity, right? That's what this is. That's what this term here is. And so we have that plus this term here. So that's what this equals here. So therefore, we have our new expression. We have our expression, which is this. Lagrangian prime equals our original Lagrangian plus q over c of d psi, full d's here, right? D psi over dt. Now, a property of this, and I'm not going to break it down, but a property of this is this term here does not affect the equations of motion of our Lagrangian. So you can write out the full Euler-Lagrange equations, and you can find the equations of motion. This will not affect it. This is just something known. And so we can actually just stop there.